Hey, we've got a Codeforces round today. Educational round 119. So let's get started. How can it be inconsistent? The only inconsistent case is 1n. Pretty sure that's it. Well, if it's 2, then no. The only case is come on. Wrong on test 1. What happened? Oh, there's no n. Alright, let's resubmit. Got it. Okay, cool. Wait, what? Okay. Does it not matter what your third point is? Zero, 1, 6. Yeah. Okay, that seems kind of silly. Alright, so what is it? W and H. I should do this just to be safe. Or let's do like side. And this is the y coordinate of 0, so this is times h. These are the y coordinates. Not that I actually need to change the variable name, but sure. Could have even done that into a double nested loop. Right? Several from 0 to b's. Okay. B string. Oh wow. Okay, so groups of stars, you should just add up their numbers. Like 2 stars is 0 to 2k. A, B, yeah. And then okay, so oh, you're writing the number in the base. Or in this. Okay. Oh, okay. That's interesting. So final length. Cool. Yeah, let's do this. Yeah, A1 star 1. A1 switch. Yep, nice. Okay, so okay, and then we're basically going to so it's just x mod x mod and then yeah. Actually, we don't need to reverse. We got pop back. Otherwise, oh, this should be B. Oops. And x divided by. Okay, so what's wrong? Oh, +1. +1. That's a problem. All right. Just missed the minute. Chips and different flavors, bag of iFlavor calls AI. 1, 2, and 3. Ooh. Any flavor, any size change. E has more songs. Wow, sorry. Oops. Wait, isn't this pretty easy? Add x to the end. But yeah, this is pretty easy. All right, I'll do E. Type is 1. Locations, text. We're going to replace all the x with y. If locations y dot size, if locations x is bigger, Oh, what happened? Oh, they can be the same? Oh, that's really silly. Oh, that was really spelled wrong. Seems like a pretty easy problem. Alright, back to D. D is just some math. Okay, so I'm going to make exactly all of the AIs with combinations of 3s, 2s, and 1s. I mean, we want to do mostly 3s. I think the only things that matter are the smallest and largest for each mod 3. Let's sort. Do you ever have 3 2s? Do you ever have 4 2s? Like if you, let's say you need to make 2 4 and 6. Oh, what if you need to make 2 4 6 8? But you can do 3 3 2 2. Can make 2 2 2 2 can make 2 4 6 8, but 3 3 2 2 can also make 2 4 6 8. Yeah. Okay. And 1 1 1 1 can make 1 2 3 4, but 3 1 1 can make 1 2 3 4. Okay. Yep. Cool. Just brute force this whole thing. Oh, I didn't close some loop. Which one? This one? No, this one. Oh, why is this? Oops. Oh, what the heck? Let's just do this. Cool. All right, I don't think you have to do that many, but why not? Let's keep it like that. Oh, I can just say it again. Let's do it. All right, times 4F or G maybe? Something more solved than G. T113. Let's define the function as the number of different strings in which at least one string. Okay, that makes sense. Yeah. They're all sorted. Oh. 10 seconds. Wow. Okay, yeah. Inversions, okay. The inversion graph is by part type. So that means you can't have an odd, like 3 cycle. You can't have this greater than this greater than this. Because then boom, 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 what's it? So longest decreasing sequence is 2. Longest decreasing sequence is 2. Should I do it or should I do G? Okay, much people got it, but these people all seem really good. Maybe F. Longest decreasing sequence is 2. What does that mean? That means we're always checking the largest number and the largest second number, and we cannot allow that to have a third. Everything after it has to be bigger. Insert the second number. Yeah, there's only two cases. Either it's a new largest number, or it's a new largest second number. Is this better or is this better? SSRS is doing G times C. Largest number, largest second number. It seems like you always want the beginning to be negative. Yeah, I mean the first number, yeah, you might as well make it negative. Yeah, so -1, and then you don't. Do you want to do -2 or do you want to do 2? So you're definitely doing -1. when you get to -1, -2, or you can have just 2. And then you get to 3, you either have you have 3, -2, or you can have 2, -3, or you can have 2 -3 is just better, right? Or we have 3 -3. 2 -3 is just better. And this is, let's use this. And you have -1. -1 is not better, so -1 is clearly better. 3, so you have -1, and then you have -1, -3, or you can have just 3. You get the 2, you can have 2, -3, you have -1, -1, -2, 3, 2, -2 is just worse. Sorry, this one's just worse. 3, -2, that's just worse than 2, -3. Is that true? There's more solves than G, still no solves than F. I have an idea. I don't know if this idea is reasonable. This. This. I think you can only have 2 states, because like here or here, and that gives you this, this, or this, this. Well, you can't have this. Yeah. Yeah, if you remember here, it's this, this, or this, this. This is better. And here, it's this, this, or this, this. This is better. This, this, or this, and this is better. This, this, or this, this. No, this one failed, and then this is better. Both failed. Yeah, so yeah, you don't have 2. There's only 2. This is a case problem. And then, oh, that's a bit annoying. How do I? state, it has high and low. It also has is this how I want to code this? It's like did get it. Okay. If high is not equal to other high, return. Yeah, otherwise and then if x is greater than high, sum dot high equals x, else sum dot low equals x. Return sum true. Right. Then P and let's call it F, whatever. If F dot no, I cannot type. Okay. Okay. So if Yes, no, yes, yes. Okay, cool. And now, time for the magic. Equals dpi plus 1 index. Yeah, is going to be s dot a. It's an output vector. A and that. All right. All right, we're still in this. Time for G. I think it's sorted. Every string is just an array of size 26, and that adds up to almost 20,000. And if you have, let's just solve the problem of how many subsequences are there, or how many strings are there. So it just has to be sorted, and the counts have to be less equal to. Do you just do that and then do no case transform? Isn't that easy? I think it is that easy. Oh, what's wrong with me? Should have done this first. Nice. Okay, and then I think I only need this. Okay, and then okay, so What is this? 223 times 3. I have to speed this up, don't I? Or do I? I can at least make this a uint 16. I don't know if that really helps. I could do something like this. Maybe this is just really fast. I don't know. Wait, ooh. What? No, that is. Oh. It's this product minus. Oh. Sorry, from 1. Oh, what am I doing? No, it's not min, it's just sum. That's not right though. Oh, wait. No, what is it I'm doing? It's like... Oh, it is kind of... Oh, wait a second. I need a bit of both of what I did. So it's not a product, it's a sum. It says 10 because it's like 2, 2, 2. What? No, what am I doing? Minus intersect 2s and plus intersect 3s, minus intersect 4s plus 4s. So what did I compute with Mobius transform? I computed... So like 3 should be... What is this, negative 3? 1 minus 2 minus 2, yeah. If that's the case, then I want to do that. I also want to... Is this what I want? I don't know how fast this is. Just do it. Hopefully it's fast enough. It's very slow. Ooh, nice. Okay. Okay, let's see if we can speed it up a bit. How would we speed this up? It's really just this part, because this is the quadratic part. So I should make some, I'll make a generator so I can see how slow it actually is. So n is 23, but like length is also a thing here. Anyway, so it takes about 3 seconds. All right, and now I'll speed this up a bit. I just need to compute mins faster, right? I don't use ways. Oh, oops. I'm using this one. Right. I also only keep this right on once. Oh, that didn't actually help. Wait a minute. Oh, I guess I can do this. Let's see. Now we use less memory. I'm not using one of the lowest in this memory. Yeah, I can get to this. And why not? Let's do it. Okay, so how do you compute mins faster? You can make an array 2 to the 23 times 26, right? Times 2 in this case. That will make it faster. Oh yeah, this is actually pretty easy. So it's like vector 16 alphabet mins 0.fill s max. S low C. Sorry, I actually need to get this back. Right, and then no, this is actually the size of them. There has to be a faster way to do the sum. Wait, at least this one faster, right? .17? Wait, this didn't make it faster? Oh wow, it didn't make it faster. Okay. mean, we can make that faster at the expense of memory again. There, that's faster. That's definitely faster. It's the fastest. What's the biggest sum here? It's like 276. Oh, that's just too big for that. How do I compute this sum in not relevant time? This should be so basic. It should be so basic. Oh, I guess I could do 2 to the n over 2 memory, which is, that's wholly unnecessary. Yeah, this is 1. Yeah, bring it on, it's much faster. I don't want to use slightly more memory, really. Yep. Yeah, okay, makes sense. I'm not sure there's a ton else to do here. We have 2 to the n times 26 times alphabet. Let's also get array size. We have 2 to the n times. I guess you can combine these into a loop. A single loop. Is that even faster? Did that get slower? It got slower. Oh wow. Okay. That's very interesting. That is simpler. whatever. All right. Is there anything else I'm gonna check out? Seems fine. Let's simplify this even more. Just for fun. This code is fine. Yeah, you just keep modding. Yep. This one is technically once ones is 3, you should do 3 on it's just better. 2's reaches. Actually, once 2 reaches 3, you can just do 1, 2, 3, which is also better. It's not better, it's the same. No, it is better, it's better. Okay. 1, 2, 3 is better. Yeah. And then for 3's, wait, let's go up to 6. Yeah. This seems like, yeah. The entire version should work. Yep. Cool. It is so simple. That's good. Cool. All right, grabbing some food and then we'll explain the solutions. Okay, we're back and there's 2 minutes left. Looks like so far only 13 full solves, mostly limited by problem F. There's actually a couple out of orders here where E was quite a bit easier than D, and actually was pretty close to C. That's a big drop from B to C, by the way. But yeah, E was easier than D, and then G was definitely easier than F. So it actually benefits you to go a bit out of order in this context. Got a couple. So shout out to Cherry Sue, who's about to hit purple for the first time. So that's exciting. I guess we'll have to wait another 12 hours for the hacking phase too. But all right, let's jump into the problems here. And let's see. So let's talk about problem A first. Yeah, so problem A, you know about consecutive pairs in your circle that are equal or not equal, and you want to know if this is possible. So first of all, if everything is equal, then it's obviously possible. You just make everything the same value. Otherwise, there's at least one not equal. And then we can, let's see, do some drawing here. Is this on? All right, now we're good. All right, so what is it? You have your, should move this here. You have your A1, A2, A3, A4, A5, for example. We can rearrange the ring so that the two ends are not equal. And then otherwise, you might have some equals, some not equals. And so all you do is you just combine the equals into a group. This is one group. This is one group. And then this is one group. And you just assign the same value to all the groups. 1, 2, 3. And that's fine. So these are not equal, these are not equal, and these are not equal. The only problem that can happen is if you have exactly one not equal and everything else equal. Because obviously that doesn't work. Everything being equal means there's only one value. And then the end, the one and end, the one and n ends don't work. So that's the only case that's a no. So code is really simple. You can actually use the C++ count function. Check if that's equal to 1. If it's 1, then it's a no. Otherwise, it's yes. All right, problem B. Oh yeah, problem B. So we've got a rectangle, and then we've got points on the sides of the rectangle. So it's something like this. Maybe I'll draw a rectangle. Oh, I can do nicer lines with this feature. Let's just pretend those circles are actually on the rectangle. All right, and there's points here, points here. You're guaranteed there are at least 2 points on each side. You want to pick 3 of them, but 2 of them have to be on the same side, and make a triangle with a max area. So let's say we're picking this as the side that has 2. We could pick this point and this point. Now, if we think about it, you know, the area of a triangle is base times height. So we just want to maximize height for the third point. So we should just pick any of the other points on the opposite side, and that will obviously maximize the height. So if we're picking 2 points here, we know what the height is. It's the height of the rectangle. So we should pick actually the 2 farthest points in order to get the biggest base. And so there's basically just 4 options. Pick the 2 endpoints on this side, on this side, on this side, or on this side. And those are all the cases. So the code also, it's nice to do this as a kind of a double nested for loop. And we're guaranteed that the x values are sorted. So we can just use x dot back minus x dot front and multiply by either h or w, depending on which case we're in. Take the max of all that, and that's the answer. All right, so that's B. Now we're on to C. Okay, yeah, so for problem C, stars can be anywhere from 0 to k Bs. So it's nice to use something called run length encoding, which is if we have, you know, star star, A, star star star, this is really just 3 stars and then 3 A's, sorry, 2 stars, 3 A's, and 3 stars. And that's the run length encoding. And what happens is when you have groups of stars, this group is going to be anywhere from 0 to 2k copies of B, and this group is anywhere from 0 to 3k. So we can treat groups of stars as being like megastars, because the reason is if you have star star, right? Then if you have B from here and you have BB from here versus BB from here and B from here, that is just the same outcome. Either way, it's BBB, right? So we don't care between those. It just increases the range of our group. Instead of being k, it's 0 to k, it's 0 to 2k. Okay, and then the next nice observation is when you have these A's and you have these star groups, for the first star group, the strings are totally ordered by the number of B's, right? So if we have 0 B's, then our string starts with AAA. If we had 1 B here, it's BAA. If we had 2, it's BBAA. And there will be something afterward, but it doesn't matter because these strings are already orderable based on those b's. So the first group of b's is the most important, and then the second is the second most important, and so on. And it turns out when we're trying to find the xth string, what we're really doing is we're just writing x in numerical form. It's kind of like base k, except it's base, a bunch of different values instead of base k. So it's like 2k here and then 3k. So if our number is, let's say our number is like 8k plus 5, then here we're going to put a, let's go with like 3k plus 5. Then this is a 1, and then this is a 5. Because there are 3k values that start with 0 here. Oh, sorry, this is actually, it's a little bit more confusing than that. 0 to 2k is actually 2k plus 1, and so on. So if we had 3k plus 1 plus 5, there are 3k plus 1 strings that start with 0 b's here, and then there are 3k plus 1 strings that start with 1 b here. And in that case, you want 1 b here and 5 b's here. So it's almost like, it's like a cross product, right? Of 2k plus 1 times 3k plus 1 times whatever else. And then we're sorting all of these lexicographically. So we're just kind of writing the number in this format. And the code ends up being, basically you do a bunch of like dividing and modding to write it in this format. You always use the last number. So in this case, you use 3k plus 1. So we're modding this by 3k plus 1, we get 5. Then we divide it by 3k plus 1, we get 1, and then that's how we get this. It's kind of like writing a number in a different base. And then we just build up that string and output it. So a little tricky, you have to like think through combining the star groups, and you have to think through this kind of weird, not quite base of number, but it ends up working out. All right, I'm going to jump a little bit out of order. I'm going to go in order of difficulty here. So since E was easier than D and G was easier than F, I'll just go in that order. So I'll jump to problem E, replace the numbers. So this is actually, it's a nice short problem statement, and this is actually a very standard problem. The main idea here is smaller to larger. So when you do this operation, that is fairly easy, but then this replace would take linear time. What we do instead is we track where are all the locations of indices that have a value of x. So that's what this array is, and when, you can see when type is 1, locations x, you need to push back n, and then increment n. So how do we do this replace? So when we're doing replace, we're basically merging locations x into locations y, right? And then clearing locations x. That's basically what this is. Insert all the location x into location y, and then clear location x. The problem arises when location x has a lot of things in it, and we're just doing a lot of work moving these vector elements into a different vector. And smaller to larger comes in right here. It's this very simple idea where, since we just want to merge these two lists together and we don't really care about the order, if we're merging a bigger list into a smaller list, let's swap them and make sure we always merge the smaller one into the bigger one. And with that, we get down to n log n time. The reason is, if you think about any individual element, anytime you do work on it and merge it, it ends up in a list that is at least twice as big, and that can only happen log n times. So this is a pretty standard idea. I think that's reflected, in the solve count here. Okay, let's talk about problem D. So problem D, we need to bring a certain set of coins so that we can make all of these values A1 through AN. The only coins we can use are 1, 2, and 3. and we need to use the minimum number of coins. So it seems like, in general, we only want to use a lot of 3s. It doesn't seem like there's a good reason to use a lot of 2s or a lot of 1s. By a lot, I mean, let's say 100 plus or even 10 plus. If we had 10 plus 1s, that seems bad, right? Because we could just have a bunch of 3s instead, and then a few 1s, and that can make strictly more numbers than we could make with just a bunch of 1s. If we actually analyze it a bit more rigorously, what happens is, let's think about 1s. If you have 1, 1, 1, what numbers can you make? You can make 1, 2, and 3, right? But we can replace this with, for example, 1, 1, 3. And with 1, 1, 3, we can make 1, 2, 3, 4, or 5. Or even better, we could replace it with 1, 2, 3, which lets us make 1, 2, 3, 4, 5, and 6. So that's just strictly better. So we should never have 3 or more 1s, is the argument that I'm saying. Because if you did, you can replace 1, 1, 1 with either 1, 1, 3 or 1, 2, 3, and you would have strictly more options out of that. And you can keep repeating that until you have less than 3 1s. Same idea applies for 2s. So 2, 2, 2, you can make 2, 4, and 6, right? But you're better off with, what was it? You're better off with, again, 1, 2, 3. 1, 2, 3, 4, 5, 6. Or if you don't want to mix 1s and 2s, if you have 2, 2, 2, 2, you can make 2, 4, 6, and 8, but you're better off with 2, 3, 3, 2, 2, 3, 3, in which case you can make 2, 3, 4, 5, 6, 7, and 8, and 10, which is strictly more again. So anyway, the point is the number of 1s and the number of 2s that you're going to pick are very limited. And the number of 3s that you should pick as a result of that should be right around the max AI value divided by 3. Because otherwise you're not going to have enough to make that. And if you do way more than that, you have just too many extra. So basically, that's all I do in my code. I just iterate the number of 1s, 2s, and 3s based on that analysis. And based on the analysis, there are only O of 1 options here. 1s can be from 0 to 2, 2s can be from 0 to 2, and 3s have to be roughly the biggest number divided by 3. I give it like a bit of wiggle room. What I submitted actually has even more wiggle room than this, which is fine because it's still O of 1. But you can be like quite tight with your bounds here. This is the number of coins that it'll take. If this isn't even better than our best, then we can just skip it. And now let's just iterate through everything in A and check if it works. The way to check if it works is actually also, you can make it kind of messy, or you can just be lazy like this, and this is pretty easy. Just loop over how many 1s we have, how many 2s we have, and then see how much we need, and see if we can cover that with all 3s from our pile of 3s. So yeah, that's the whole logic, and in that case we just output the best. This is actually O of n time. I guess this is n log n, but I don't actually need to sort, I just need the max. This is O of n time with a constant that is something like, what is this? I don't know, it's like, maybe it's like 100 times n or 50 times n, but it's still O of n. All right, so that's D. And let's skip F and go to G for now. Oops. Oh no, I lost all the problems. Okay, well, I guess this works. It's funny that this works and the other one doesn't. Anyway, for G, we've got a bunch of sorted strings, and we want to know for every subsequence. Okay, for every subsequence of our strings, how many strings are there that are subsequences of at least one of our chosen strings? So there's like multiple levels of subsequences here. And if we analyze it, because the strings are sorted, anything that's a subsequence is going to have to be sorted as well. So we just, every string is really just a 26 tuple. which is, you know, count of A, count of B, count of Z. And that's basically a full description of a string. And one string is a subsequence of another string if and only if the condition we need is C is a subsequence of C prime if and only if this is true. And that's fairly obvious when you think about it, because if you take a subsequence of the C prime string, you're just grabbing some amount of the A's, some amount of the B's, some amount of the C's, and so on. So now, what happens if we have a group of strings? How do we know whether we can how many strings we can make as a subsequence of at least any one of them? Well, we can add up the counts for each string. The number of strings that are subsequences of any particular C is just this product. Because we're choosing between 0 and CA A's, between 0 and CB copies of B, and so on. We can add all these up for our subsequence. But the thing is, we're overcounting, right? We're overcounting strings that are subsequences of more than one of our strings. So we can use inclusion-exclusion here. So let's say if we have let's say we have 3 strings, right? C1, C2, C3. And then P1, P2, P3 are the products, are these products. We do P1 plus P2 plus P3 as our approximation. Well, we need to subtract subsequence of C1 and C2. You know, C2 and C3, C1 and C3, but then we need to add back subsequences of all 3. And this is just inclusion-exclusion. So yeah, this actually gives us an algorithm, because in order to do this operation or count this operation, we're actually just going to take min C1A, C2A, C3A plus 1 times and so on. The reason is, how many A's can we have and be a subsequence of all 3 of these? It has to be less than or equal to all 3 of these values, and that's why we take the min. So we can compute this. This gives us kind of like a 3 to the n approach, maybe 3 to the n times the alphabet size, which is obviously too much because that's 23. So we use this idea called the Mobius transform. Mobius transform is the inverse of something called submass sums. Some people also like to call it sum over subsets. And it takes n times 2 to the n time. And it basically does this operation for us, this inclusion-exclusion for us, for every mask in n times 2 to the n time, which is really nice here. So that's kind of the key algorithm that we're using. This is just jumping into the code. This is input, counting the occurrences. This is computing the mins for a mask right here, and then taking the product. Then we do the magic here with the Mobius transform. There's a little bit of parity fixing because sometimes we want the opposite parity from what the Mobius transform wants in terms of which ones we make negative and positive. So we have to flip some of them to negative. And then once we're done, we just compute our answer using the formula they asked for. So that's pretty much G. The runtime is going to be 2 to the n. This is the worst part. 2 to the n times alphabet. And the memory is just to the n, which is nice. There's an optimization you can make where you improve the runtime to just be 2 to the n times alphabet, instead of 2 to the n times alphabet. But that makes the memory end up taking more space. It turns out they give you 10 whole seconds here and a whole gigabyte here. So either of these ends up being fine. You can either this is the 2 to the n, or this one rather, is the best one. 2 to the n times 26, and you can see the memory is quite low. Or you can use more memory and get it to be faster. This is the 2 to the n times 26. All right, one more problem to talk about. That is problem F. So yeah, so this was the hardest problem in the set. Only about 18 solves is what I'm seeing here. Although, is that including, that might be including unofficial submits. Let's see. 16 solves, yeah. And 13 full solves in total. Yeah, and then this problem, we have a permutation, and then we're going to make a graph. The graph, basically every inversion in the array, I less than j and ai greater than ij, ai greater than aj, is going to be an edge. And we want this graph to be bipartite. And we want to figure out if we can basically negate some of the values in the permutation to make it bipartite. So first, to drill down into this bipartite condition, in order for graphs to be bipartite, it's bipartite if and only if it has no odd cycles. And if we think about that in terms of inversions, then we're just not allowed to have a sequence where I less than j less than k and ai greater than aj is greater than ak. Because that would be, there would be an ij edge, a jk edge, and an ik edge, which is a 3 cycle. And if we think about, larger cycles, we can just make sure that we're good by avoiding 3 cycles in particular. Because otherwise, if we have longer paths, we have to end up having a 3 cycle somewhere. So our goal is going to be to avoid 3 cycles, or in other words, avoid a decreasing sequence of length 3. Or in other words, the longest decreasing sequence is at most 2. This is like LIS, longest increasing sequence, but now we're doing decreasing. If you prefer to think about increasing, you can reverse the permutation, and then you can think about increasing. But we're going to do it with decreasing. So now if we think about the longest increasing or decreasing subsequence algorithm, the idea is it's kind of a DP on what is the best ending for any length of sequence. So in particular, for longest decreasing sequence, at most 2, that means we're going to have 2 values in our state. One is the largest ending of a subsequence of length 1, and then the largest ending of a subsequence of length 2, of a decreasing subsequence, right? This is just the largest value so far, pretty simple. This is the largest value less than something before it, right? This is a tuple of 2 values that makes up our DP state. So basically, if we go through a prefix of the array, of the permutation, and we decide some of them are positive, some of them are negative, the only thing we care about afterward is this tuple, this state, because of how this algorithm works. And for our purposes, we don't want to ever add a 3rd element here. So some states are better than others. In particular, let's say you have, so first of all, A is always greater than B in this state. I'll just leave that there actually. If you have one state that is 8, 5, and you have another state that is 4, 3, then 4, 3 is always better than 8, 5. Because 4, 3, in particular, 4 is less than or equal to 8, and 3 is less than or equal to 5. What that means is 4, 3 is always going to be better at avoiding a 3rd element than 8, 5 is. Anything that makes a decreasing sequence of length 3 when you have a state of 4, 3 also makes it for 8, 5. In fact, there are more things that make it for 8, 5 than for 4, 3. In particular, if you added a 4 to the end here, I guess 8, 6. If you added a 5 to the end here, that would make a problem here, whereas it would not make a problem here. So if each corresponding value is less than the other state, then this state is strictly better than this state. Okay, so one algorithm we have then is we can just go through our elements one by one, and then consider the states that we would end up having by adding either pi or negative pi, and then we would end up with a bunch of different states. And in fact, we can do this with all the states and get to the end. We'd have 2 to the n different states in the worst case. Some of them would be invalid though. For example, we can't add a 2 here because that would make a decreasing sequence of 1, 3. So that would be considered invalid. So yeah, we would have potentially 2 to the n states by the end. And based on that, we can determine whether or not there is a way to make a longest decreasing sequence of length at most 2. And we would want to backtrack through those states to actually construct it. So obviously 2 to the n is not a good idea here because n is a million. But one obvious optimization you can make is you can just throw out the states that are, suboptimal to other states. So in this case, if we had the 2 states 8, 6 and 4, 3, we would just throw out 8, 6 and only have 4, 3 based on what we talked about. Another example of this is in the beginning. When you start with 1, your options for states are either 1 and negative infinity, and the second value is going to be negative infinity by default, or negative 1 and negative infinity. And based on what we talked about, this one is always better than this one, so we can throw this one out, and we just have 1 state. Yeah, so we can kind of do this through the whole array. Take our dp states, consider adding p or negative p, which is what we're doing here, and then have those states, and then prune out the bad states, and then go to the end. So that seems better than the 2 to the n, but it's not clear how much better. It turns out if you do this, this is actually O of n time. This actually gets you down to linear. And the reason for that is you never have more than 2 states, ever. Basically, if we think about, let's think about a number line, right? Where the number line is something like this, and we have 2 states right now, right? One state. Basically, this is, if these are a, b tuples, then this is the a value and this is the b value on the number line. So basically, I'm representing these states as intervals. Let's give a little bit more room. Okay, so if we have 2 states, they have to look like this, right? Because if you had the other state looking like this, well, this state is strictly better than this state. Also, the numbers increase from left to right. So this is like, these are like negative infinity this way. Like, it's not actually negative infinity, but you know what I mean. These are negative numbers here, positive numbers here. This state is just strictly better than this state. So the only way to not be strictly better is for one to contain the other one. And now it's ambiguous which one is better, right? But now if we think about what is the, basically there are 2, every time we get a new number, there are 2 options that we can add. And my claim is for each of the options, only one of the states ever makes sense. And we can just think about it via the where on the number line the next number is. So let's say the next number is here. Well then, if we think about these 2 states, this state would turn into, basically this number would replace this number, and then this number would also replace this number. So these are the 2 options we end up with. But this one is strictly better than this one because this value is less than this value. So only one of these is worthwhile. Another case is the number is in between here. Oh man, I gotta, let's see. Okay, the number is in between. In this case, you will end up with this result. It will replace the second number. And in this case, it will replace the top number, so you'll end up with this result. And again, this state is strictly better than this state. So only one of them makes sense. Now let's think about a number that is in between these two? Well, now in this state, you will end up with this, and in this state, you will also end up with this. And then this state is strictly better than this state. And you can just go all the way down. If you go actually even further, when you start to get to here, this state cannot add this number because you would have a longest decreasing sequence of 3. So only this one is valid. And when you get down to here, neither of them can add it. So there are 0 options. So the point is, for each of negative p and p, you will only actually generate at most one state. So assuming you have, or no, just in general, yeah. So you'll never end up with more than 2 states in your DP array. And that's why it is constant time per element, and it's O of n overall. You just need to be careful in implementation to actually track which state you came from and what the last value was. And I just kind of set all that up here and then backtrack the index, the value, and the previous, and so on, and then that gets me the answer. All right, so yeah, this was a, okay, got it. This was like a fun little problem. A bit tricky. Definitely this constant state idea is not super common, so a bit tricky. G was definitely a much more standard problem with the Mobius transform idea. But yeah, I mean, I think that showed up in the results where, you know, the number of solves on F was 1/6 as many as G. So yeah, fun little problem set. But that's going to be it for me for this video. I hope you liked it. If you want to check out future videos, make sure to subscribe to the channel, and I'll see you in the next video.